All right, we're getting ready. I gotta get my... All right. Welcome, everybody. Welcome to another IAEI News Live. My name is Thomas Dimitrovich. We got Steve in the house. This is very welcoming topic. The qualified persons will not be around when those cooling systems fail. We're going to get into those discussions, Steve. We are going to. Laurel, research is in the house. Looking forward to today's discussion on medium voltage. Yes, it should be interesting. And you know, hey, Michael, the stimulus for this session came out of Philly. And where were you, Michael? I missed you, brother. They said you were probably smoking a cigar and having a scotch somewhere. So I don't know. But anyway, I need to put my phone on stun. Where's my phone on stun? Boom, there it is. Okay, so we are going to talk about medium voltage applications, but I wanted to first say, did you get your copy of this puppy? The 2026 analysis of changes. Did you get your copy yet? I mean, if you've gone to I know the Western section, that's where I got mine at, the Western section. Did a program on that, and I think there are other sections that we're going over the 2026 analysis of changes, but you got to get your copy of the book. PowerPoint's coming out shortly. I put a link in the description for the analysis of changes, and I'm going to put it into this chat box. There we go. So I know it's going out on YouTube, and if you're watching this on LinkedIn, don't forget to check the description for the event on LinkedIn, and or you can come over here to the IAEI's YouTube channel and subscribe. So, you know, Laurel always says it well, don't forget to subscribe. So anyway, it's out there on Facebook and I see it posted to Facebook and to YouTube. I'm not sure about LinkedIn. So hopefully it will get to LinkedIn as well. So I want to talk about medium voltage transformers. We're going to hit this discussion of medium voltage transformers now. Again, get your copy today. They're out there, and the quicker you get up to speed on what's coming, there's also some relief in the latest code. So hopefully your state adopts the National Electrical Code. I am going to be talking out of the 2023 edition of the code. My 2026 edition is over there, so it's a little bit too far for me to reach. Just having a little hard time reaching. Okay, so I also want to tell you, since I am out of the West Virginia chapter, we are registering for our November event for the West Virginia chapter of the IAEI, and we're going to have Mr. Brian Bowman in. Brian is going to cover the interconnected system. So we're going to talk about solar. We're going to be talking about photovoltaics, energy storage systems, generators, you name it, wealth of information. And with Brian Bowman, it's an all-day event. We serve lunch as well. So I get to talk about the West Virginia chapter because I'm the one going live. All right, so let's talk about, I got a notification on LinkedIn. And hopefully that's a good thing. Okay. All right. Let's talk about medium voltage transformers. I was in Philadelphia last week. And we were doing, it started out as part 2. Hey, good morning, good day. Excellent, good day. Maritza Ramos. I'm not sure if that's it. Laurel's got her copy. Excellent. And there's the link. If you don't know what it is, that's the link. So last week I was in the Benjamin Franklin chapter, and I saw a lot of good friends. Andrew Casnay. Andrew, I am going to need your help, buddy, because this topic came out of this meeting last week, and we were going over transformers, talking about the primary and secondary, and we had some extra time, and I said, let's take a look at a medium voltage transformer. And I threw a nameplate up, Andrew. I threw this nameplate up. And you'll notice a couple things on this one. We have the kVA is 3750/5000. We have a class AAFA, which we're going to talk about what those are. Primary is 4160, secondary is 480, 277. Whoop. They give us the low voltage amps. The impedance is 5.92. Now I have 2 kVAs, but I got 1 impedance. We're going to talk about that. But when I look at this book, if I go to, I got to be careful because my other glasses are upstairs. These broke. If I go to Article 450 on transformers, and in 450 on transformers, when we talk about table 450.3a is your maximum rating or setting of overcurrent protection for transformers over 1,000 volts. So we had the discussion that when you have a transformer that has a primary of, say, 4160 in this case, secondary of 480, I know when I was really fresh out of college and having not, I did an internship, and I did a systems analysis study and a selective coordination. So I did a short circuit study and a selective coordination study for power systems development out of Canton, Ohio. And I was working there, and the president of the company gave me a project for Union Carbide down in West Virginia. And I did a short circuit and a coordination study, and it was 2300 volts. There was a lot of 2300 volts. There was this big zigzag transformer, a lot of delta. But that was my first step and taste of power systems engineering. Then I learned quickly that when you get into a 4160 to 480, I was initially confused, thinking, well, for the 480 volt side, do I go to table B? And for the 4160 side, do I go to table A? Or do I stay in table A because one side of this transformer is medium voltage, so I treat the entire thing, and that's the right answer, right? So if one side of this transformer is greater than 1,000 volts AC, then you're into medium voltage, and regardless of what that secondary could be, 208 volts, whatever it is, 209, whatever it takes, it doesn't matter. It's still a medium voltage transformer. So and they do it backwards. In all the other articles of the code, medium voltage, say they do low voltage first and then medium voltage is last. Low voltage first, medium voltage is last. Not tables 450.3, because A is medium voltage and then B is your low voltage. So, regardless, right? So, I know I have these requirements in 450 for a medium voltage transformer, they talk about sizing the primary overcurrent protective device and the secondary overcurrent protective device, but they don't, Andrew, they don't tell me how to handle a transformer that has fans and it has 2 kVAs. Which kVA do I use? And if you look at this is what you'll see from a fan's perspective. So there's racks and there's mounts and there's controllers for fans to be added to get the higher kVA rating out of it. Now, the transformer cooling, AA means ambient air. So that means that the ambient air around that transformer is used to cool the transformer. AAFA means fans have been added, and the fans are there to manage the heat in the transformer to make sure that I can keep it cool, and that means I can push more kVA out of it, right? And then there's this FFA. I might have an AA/FFA or whatnot. That's future fans added. That means that the transformer has provisions for future fans, for the addition of future fans, but it wasn't shipped with those fans. So I might have something like this, and it says AA/FFA, which means I can't get 5,000 kVA out of it unless I add those fans. So one of the questions I have in my head is, well, what does the code say about these future fans being added? Do I have to add, or do I have to equip the conductors and the overcurrent protection to accommodate the 5,000 kVA, anticipating that I might add fans? Or can I just size everything based upon ambient air, the lower kVA, and say, you know what, it's not my problem when they want to add fans to get 5,000 kVA. You'll probably trip the primary overcurrent device on overload, but hey, not my problem. So the code does, I don't believe, Andrew, correct me if you think I'm wrong, but I don't see any provision in Article 450 to address the higher kVA versus lower kVA and give me direction on how to use and apply Table 450.3a, which is the maximum rating or setting of overcurrent protection for transformers over 1,000 volts as a percentage of transformer current rating. So what it's, now the table tells you that you have limited, let me call up NFPA link. Let me show you something. NFPA link. Andrew, no. Where is my NFPA link? So they don't address this. Now, if I bring up, I'm going to bring up NFPA. Oh, let me see if I can do this. I'm over here, baby. I'm over here. So if I bring NFPA 70, 2023 edition, I have to log in. I'm going to use, I don't want caps lock. I got to put my, I never had to do this before. Thomas A. Dimitrovich at Eaton.com. There we go. There it is. Now I can use my finger. Okay, so let's go to Chapter 4 because it is equipment for general use, and that's what a transformer is. I'm going to go to 450 for transformers. And then I'm going to scoot down here to 450.3a. And I'm going to blow this table up, and I want to tell you, I don't need to, oh yeah, I do. So I learned this, I learned this during one of my live streams. And I'm telling you, it was a godsend. Pin header. Whoa. Now the header stays, and I love the way they shade below this line. So when you're using your edition of NFPA link, don't forget about pinning and unpinning the header when you open up tables. It is phenomenal. All right. So I have primary protection over 1,000 volts. And then I have a line here for when the secondary is over 1,000 volts and when the secondary is less than or equal to 1,000 volts. So we address both situations. Now, I'm not sure if there's a delay. Do you see a delay here? I'm sort of thinking that I'm getting a delay out of this camera, but I'm not sure. But in any case, this table is giving me the option to go when my secondary is less than or equal to 1,000 volts. And that's the indicator that regardless of whether or not you have a low voltage side to a transformer, you are still in table 450.3a. Even though one side is medium voltage and the other is not, the entire transformer is covered under 450.3a. So I thought so, Laurel. I thought there was a tiny delay in there. But in any case, if you look at this table, it gives you the percentages when you have a circuit breaker or a fuse, because in many medium voltage applications, I may have a fuse rating, a medium voltage fuse protecting the transformer. And then they also key off of the rated transformer impedance. Now, on this one here, my impedance was 5.92%. So if I looked at the table, so Dawn Ganir is saying, that they moved the table to 450.5a. And you know why probably, Dawn? It's probably because, 450.2. Well, 450.2 is the interconnection of transformers, and 450.3 is overcurrent protection. So and 450.1 is scope, which it should be, but .2 and .3 are reserved now, so we probably moved everything up by 2, which means table 450.3 is now 450.5 because 450.2 is listing requirements, 450.3 is reconditioning requirements, so everything bumped up by 2. Wow. That's going to throw everybody's documents off helter-skelter. Okay, so, but in any case, my impedance here is 5.92, and in this table, it has not more than 6% impedance, so I would follow this line item, any location. If I'm in a supervised locations only, and they have a 3, a supervised location is a location where conditions of maintenance and supervision ensure that only qualified persons monitor and service the transformer installation. So they give you in the informational note a little bit more information regarding that supervised locations. And then it tells me that if my impedance is not more than 6%, which is the case that we have here, for a circuit breaker, I can go up to 600% on the primary. For a fuse, up to 300%, and there's a note 1 where the required fuse rating or circuit breaker setting does not correspond to a standard rating or setting, a higher rating or setting that does not exceed the following. So remember, in low voltage applications, they are saying in a low voltage application, I could not exceed this maximum rating. What they're telling me for medium voltage, they're putting me up to 600% on the primary and 300%, 600% for breakers, 300% for fuses. And they're saying a higher rating or setting is permitted as long as it doesn't exceed the following. One, the next higher standard rating or setting of fuses and circuit breakers, 1,000 volts and below. And then if it's medium voltage, the next higher commercially available rating or setting for fuses and circuit breakers above 1,000 volts. So I can go to the next higher when it's a medium voltage application, but I can't do that at the 250% for a low voltage transformer. So there's I think it's a big difference in application of the tables between A and B. Laurel is saying in the 26 table, is over 1,000. Yep, it's still the same. So they didn't change the order. They still have medium voltage first and low voltage second, which is backwards, but that's okay. So, all right. Okay, so queso, isn't that a cheese? I think that's a cheese. All right, so we have 600% permitted for breakers on the primary, 300% permitted on the secondary. Okay, and then on the secondary, since I'm not more than 6%, on the secondary, I have 300% for a breaker, 250% for a fuse if it's over 1,000 volts. If it's, say, in this case here, we're at 480 volts on the secondary, and I know that because of right here. I don't know if you can see, you can't see my mouse, but right under the kVA on the top left-hand side, down 1, 2, 3 lines, it gives me my the voltage on the secondary. I'm at 480 volts, so it tells me for a 480 volt, in this case 480 volts, the table's telling me I can go up to 125% with the same thing. So for 1,000 volts and below, the next higher amp standard rating or setting for fuses and circuit breakers is permitted above the 125% on the secondary. But I think the big difference between the low voltage and the medium voltage in this case, based on that in 5.92% impedance, on any of the impedances, on above 1,000 volts, it tells me I can go to the next higher commercially available. Ooh, wow, I almost missed that. That's a big difference. Think about this. What is the difference between standard amp? Can I zoom in on this? Can I? I can't. Whoa. No, I can't. So think about this. It says in note 1, take a look at down below where you have 1 and 2. 1 says the next higher standard rating or setting, and 2 says the next higher commercially available rating. Check that language out right there. I know it's kind of hard to see, but I'll just speak to it. So the difference of that is when I see the words standard rating, that means I'm going to Article 240. And I believe that would be 240.4, right, Dawn? Help me here. 6. 240.6. I always get 4 and 6 mixed up. 240.6 is titled Standard Ampere Ratings. So anytime you see the next higher standard ampere rating, that means you are governed by the table in 240.6. But when you see the next higher commercially available, that means that if I look at a manufacturer's list of what they offer, and let's say the next standard ampere rating goes from 100 to 200, just making numbers up. Let's say it goes from 100 to 200 and you're at 145. If the manufacturer makes 150, you got to go to that one, not the standard ampere, which would be 200. Make sense? So now what's Dawn saying? The scope of 240 is 1,000 volts or less, so its standard size is in 2. Oh! Yeah, well, that's what it says. It says the next higher standard rating or setting for fuses and circuit breakers 1,000 volts and below. And then item 2 says the next higher commercially available rating or setting for fuses. So even if there was a table in 240 that applied, it wouldn't apply because you have to use the next commercially available fuse or rating. Andrew says that was done for commercially available since there was not a standard for, oh, that's right, exactly. So the 240, and I think that's Dawn, I think that's your point, is that the less than 1,000 volts, the 1,000 volts and less overcurrent protective device standard ampere ratings are governed, and they're in the standards. What Andrew is saying, and I think, Dawn, what your point was, correct me if I'm wrong, there is no standard, so there would not be a table in 240. So they basically say the next higher commercially available rating, because that could be that's what's available from the manufacturer. Dawn says there are no standard sizes in Article 245, so use the commercially available sizes. Right. So there, and that would be and the reason Dawn is bringing up 245 is because 245 brings up medium voltage, and to Andrew Casnay's point, you don't have a standardization of ampere ratings like you have in low voltage for medium voltage. And in 245, it's a very short article, you've got the scope, you've got reconditioned equipment, circuit interrupting devices, feeders and branch circuits, and then additional requirements for feeders. That's your overcurrent protection for systems rated over 1,000 volts AC, 1,500 volts DC. So it's pretty cut and dry. But so you got to go back to what the manufacturers offer. Yep. And you know what? There was an Article 245 in the 2023 edition, Laurel. Now let's take a look. I'm going to take a look at the 2020, the 2026 code. If I look at the 2026 code, I've got Article 240, and here's 245. So here's the 2023 code, and here's 245. It's pretty short. Let's do this. How do I get back to chapter 2? There we go. So I got 245 in the 2023. I've got 245 in 2026, and I have scope, listing requirements, reconditioned equipment, adjustable relays and trip units, circuit interrupted devices. Ooh. I didn't have adjustable trip units, did I? 245, 246, whatever it takes. 245, I've got, yeah, I didn't have, that's a new section. What does adjustable relays and trip units say? Where settings of relays or trip units can be adjusted, documentation of the settings shall be available to those authorized to design, install, operate, or inspect the installation and the AHJ upon request. So the key thing there is that we have some guidance, but the point that Dawn made and Andrew made and Laurel's making, hey, I don't have any standard ampere ratings in there. And I lost my other camera, so no big deal. Okay. I knew something was going on over there. I don't know if it's the power. It might be the power. I may have run out of battery. I may have been on battery. All right, so so I'm going to be applying 450.3a for protection of this transformer. And remember, the primary protection gives me my short circuit protection for the transformer. My secondary protection is going to give me my overload protection. I could, I don't have, the only place I have where I don't necessarily have to have, well, not necessarily, where I don't have to have secondary protection is in supervised locations only on medium voltage applications, and for any impedance when my primary circuit breaker is at least 300%, and again I can go to the next larger based upon the commercially available, 300% and 250% on fuses. Okay, so, and remember the process. The process is you will first get the information from the transformer. You'll determine the full load amps on primary and secondary. Then you'll use this table. Now, let's say, for example, I'm dealing with this transformer that has 2 kVAs. The kVA on the primary for 3750 is 3750. So let's calculate what's the full load amps. Let's walk through it. 3750 divided by 3 square root divided by 4.16 is 520 amps. All right, so that's at 3750. I've got 520 amps. I need to write this down. 3750, 520 amps. I'm going to move this over. I'm going to move this over here. All right, so 520 amps at 3750 primary. Then if I'm at 5,000, I take 5,000 kVA, divide that by the square root of 3, divide that by 4.16, and that's 693 amps. 694, it's 0.9. 694 amps at 5,000 kVA primary. Secondary, I'm going to be either 4,511 or 6,014. And that's on the nameplate, low voltage amps. Let's just do it. 3750 divided by square root of 3 divided by 0.48 is 4510.54. So they round it up. 4511 amps. And then we'll do the 5,000 kVA. 5,000 kVA, divide that by 3 square root. Divide that by 5,000 kVA. Divide that by 0.48. Boy, is 6,014. So that's the same. 6014 amps. So what you can see is that I've got to make sure that I have overcurrent protection and the size of the conductors to handle that 5,000 kVA, because I'll have different full load amps. And if I'm gearing my overcurrent protection off of the full load amps out of table 450.3a, or if you're in the 2026 code, 450.5a, then my overcurrent protective devices could be larger. Ooh, they could be larger. My conductors would have to be larger. But I had a really good question asked, and it was asked after we got into the discussion of the impedance. So if you look at this nameplate, I don't know if I can do this. Can I? Yes, I can. The impedance on this nameplate is 5.92, yet my kVA is 3750 and 5,000. Why do I only have one impedance? And the reason that is because adding fans or not adding fans has no impact on the impedance of the transformer. The impedance of the transformer is based upon the physics and the construction of the equipment. So that would be the core and etc., right? Whether or not I cool this thing to be able to add more load to it doesn't mean make a bit of difference in the impedance. Now, the impedance doesn't change, nor does the inrush current for this transformer change. So when I think about the primary overcurrent protection, what do I worry about? I worry about the inrush current, so I can energize the transformer. Beyond that, and I'm worried about short circuit protection, right? So that's why I have these maximum values, which hopefully you probably wouldn't go all the ways up to 600% unless you've got, I don't know. There are probably reasons. But my overcurrent protective device has to permit the transformer to energize, and I'm going to see that inrush current regardless of whether or not I have a load on the transformer, because that's the magnetization. That's just getting all of the getting physics to happen, right? Hysteresis, the whole bit for the iron. So my impedance is not going to change based upon whether or not I have fans. My inrush current's not going to change based upon whether or not I have fans. So I have the ability to pick an overcurrent protective device that that would work for both with and without fans. I've got to think about with and without fans is my point. Now, if this was FFA, future fans added, there's nothing in the code that tells me I need to size my overcurrent protection and I need to consider the higher kVA, this 5,000. If this was future fans saying, look, if you add fans in the future, you can get up to 5,000 amps. There's nothing in the NEC that says I have to accommodate that 5,000. Even if I have the potential of putting fans. And I would love to know if you guys think that we should. My gut's telling me, and if I look at, I'm just trying to see if there's installation over 35,000 volts. There's nothing in here that speaks to, they speak to transformer volts. They have oil insulated transformers outdoors. And that's basically dealing with the oil insulation. But there's nothing here about fans. In fact, you know what? The other thing we can do, I'm gonna go to 450 in NFPA link and search for the word fan to see if there's anything in 450 that uses that terminology. Ventilation shall dispose of transformer full load heat losses without creating temperature rise. So that's ventilation. In 450.11, they talk about ventilation openings, ducts, marking, the required clearances. That's all about clearances. 450.45 is ventilation openings. 450.41 is talking about location. It's all about ventilation of for around a transformer. There's a lot of use of the words. I just typed in fan and it's got a lot of hits. Dry type transformers installed outdoors. We already talked about that. Any overcurrent sensing device shall be provided with the cause main. And overcurrent, what is this? This is a 3-phase 4-wire system. Grounding transformers. That's grounding transformers. Yeah, I don't have anything in here that deals with how to handle sizing of the overcurrent devices. So the question would be, what does this say? Yeah. Hold on. Fan. I'm just doing searches in. You know what's funny is I think it's finding the word fan in the. When I type in fan, just searching the page, I don't get anything. When I type it in the search engine for NFPA link, yeah, FAN. I'm not sure. Yeah, I don't know why it's finding it's finding requirements, but there are no requirements in 450 that use the word fan. So the question that I would have for the team out there is, how do we size those overcurrent protective devices? When you have if you think about the way the terminology, let's get back. If you think about this, you can have AA, which is ambient air, AAFA and FFA, future fans added. That's the one that bothers me the most. Future fans added. I think if you had AAFA, there wouldn't be a code requirement. I mean, I don't have a code requirement that says I have to accommodate the 5,000. In fact, it's vague. It doesn't say anything about the temperature rating. Andrew says, the nameplate temperature rise, this is more than I would accept. Would we need to consider higher rated temperature conductors? Oh, so Andrew, here's my thoughts on that. You're looking at this temperature rise up here, right? That's a good question, Andrew. That's a good question, Andrew. I'm not sure the answer to that question. I know this temperature rise is of the transformer itself. Your question is, would we need to use a higher rated temperature? And I don't know the answer to that question. I'm going to take that down as a note. Andrew, I can always rely on you for equipment that has a temperature rise of 80 degrees C. Would we need a higher rated conductor? I mean, we got 90 degrees C insulation. Temperature rise is 80 degrees C. I don't think you would have to change that. I don't think you would have to do anything special there, Andrew, but I'm not going to say you don't because I have not. I've got to do some homework there. Don Ganir says the impedance stays the same when you add fans, so sizing the OCPD for base kVA is permitted. It's permitted. It may not work. It's permitted. And the reason I say it may not work, Don, is because, remember, kVA is full load amps. So if I have 5,000, well, I have the numbers here. So on the primary, at 5,000 kVA, my full load amps is 694 amps. If it's at 3750, my full load amps is 520. Now, if I did a percentage of 520, yeah, it's not going to, it's, I think to your point, 694 full load amps is not going to trip the primary overcurrent device on long time pickup. Because if I did a 520 amps, yeah, it's not going to make a difference. If I did 520 amps and I did a 1.25, I'm at 650. Ooh, I can't do 1.25. I can't do 125% on the primary. If I did 125% on the primary and picked a 650 amp overcurrent device, not a 600 amp overcurrent device. If I picked a 600 amp overcurrent device, or what's another? I don't go to the standard ampere rating. So if I had a 650, I'd have to look and see what the manufacturers. I have to make sure that I can pull 694 amps on the primary. Period. And I have to make sure that is. If I'm medium voltage, I don't have the 80% issue. It's all 100%. So I have to at least make sure my primary overcurrent device will permit 694 amps to flow. If I have an overcurrent device that's less than that, it may work on the 3750 kVA, but it's not going to work on the 5000 kVA. I don't care about the short circuit protection because to your point, the short circuit protection is the short circuit protection. But it's the overload that I'm worried about. I'm not worried about inrush because inrush is not going to change. I should at least make sure, but if I'm at, what am I permitted? I'm permitted up to 600% on a circuit breaker. So if I did 300%, if I did 3 times 520, I'm at 1,560. So my primary overcurrent protective device, which is only there to provide short circuit protection, is going to be much greater than the full load amps on the primary. Now on the secondary, here's the question. On the secondary, if I'm permitted on the secondary up to 125% of the full load amps on the secondary, if I say I'm going to do 125% times 3750 times the full load amps at 3750, which is 4511, that's 5638. I can go to the next higher. So my equipment on the secondary wouldn't be able to exceed that. But if I'm at 5,000 kVA, I can put more load on it. So my equipment on the secondary, my secondary overcurrent protective device could theoretically be 1.25 times 5 times the 5,000 amp secondary, which is 6014, and now I can go up to 7,500 or the next larger. So Dawn, I may not have to worry about it on the primary, but on the secondary, I can pull more load. And I could supply more load from this transformer. So picking my maximum size overcurrent device would be impacted based upon the kVA and the fans added, because my overload protection is on the secondary. And if I have fans added, but what if I have future fans? I can't size my secondary overload protection based upon future fans at the 5,000 kVA because I don't have the fans on there. So I would have to be mindful of that and make sure I use the lower kVA unless I added those fans, because the fans are there for the overload of that transformer. So I think the significant important decision that needs to be made is on the secondary. I don't have any prohibition that I can't use the 5,000. I guess there would be, because I don't have fans if it's a future fan added. It's my overload protection I'd have to think about. Andrew says he typically sees 55, 65 degrees C rise. Yeah, but your insulation of the conductor is 90 degrees C. But I'm not sure of the relationship between that temperature rise and the insulation. I think your insulation of your conductor has to be greater than that temperature rise of the transformer itself. And if I'm using 90 degrees C insulation, then I don't have to worry about it because I'm not exceeding the 90 degrees C insulation. But I need to do a little bit more homework on that question, Andrew. Leave it to you to stump me. You did. The temperature rise is for the internal windings, not for the primary and secondary bushings. I see no need for any conductor change. So you're saying that you would not see adding larger conductors on the secondary because I have more full load amps. I can provide more current. You have to. You can't put, if you have 5,000 kVA and my secondary full load amps goes from 4511 to 6014, and if I protected it at 4511 and I'm protecting the conductor at 4511, or say 4,000 amps, I'm never going to get the 6,000 amps on the secondary. So I would have to, Don. You would have to. I think you're wrong. That's just my opinion. Vince B, that temperature rise is added to the ambient. That is stated as 30 to 40, so I would say yes, the higher temperature needs to be addressed. Vince, you're probably right. I definitely have to do more homework on that. I'm going to go with your lead, Vince. You sound a lot smarter than I do. Dawn says the secondary protection of conductors will be based on the actual calculated load. If my load is only 100 amps, well, yeah, of course. But you wouldn't be buying a 5,000 kVA transformer if your load was only 100 amps. And you would definitely not be adding fans to get more kVA if your load was less than the 6,000, because you wouldn't need to pay for those fans. So if my load was actually less than 4511, then why would you invest in a 5,000 kVA with fans? It just doesn't make sense. The financials don't make sense, Dawn. So I'm thinking that if you spent money to buy a transformer that can go to 5,000 kVA, if you didn't need more than 3750, you wouldn't have spent the money for it. That's just my gut. And if you spent the money for 5,000 kVA, then your conductors on the secondary have to be able to accommodate the additional load. Whether it's all in one, if you bought one piece of gear, switch gear that can handle whatever amps, or two pieces of switch gear, I don't know. You're allowed 6 disconnects up on the secondary, right? So I can, and the disconnects can't add more. So your overcurrent protective devices can't be larger than the summation of your full load amps on the secondary. So I'm just saying that if you bought 5,000, if you paid for fans to get to 5,000 kVA, it would be foolish to say you don't need to have equipment size to handle that kVA. Whether it's all in one conductor or multiple conductors, regardless, you did it for a reason. That's just my gut. I don't know. I could be 100% wrong, but that's my gut. All right. So I've got to do some homework on the temperature rise discussion and the conductor. The relationship between temperature rise of equipment, and I would say, Andrew and Vince, this applies to any piece of equipment. The relationship of temperature rise to conductor insulation rating. That's a good discussion point and all that good stuff. I think we feel comfortable knowing that the impedance doesn't change, the inrush current doesn't change. My primary overcurrent device at 3750 will probably, based upon these percentages, will probably accommodate the 5000 kVA. So primary protection, less of a concern. Secondary protection, I'm getting more kVA. I can put more load on this transformer, whether it's in a single unit or a single low piece of switch gear or multiple switch gear, whatever. We know that available fault current is full load amps over the impedance times 100. So my secondary fault current, I'm going to use the 3750 to determine the secondary fault current and not the 5000 regardless, because my fault current is going to be driven off of, it doesn't, the fact that I have fans does not change the available fault current on the secondary. So when I think about the fault current on this transformer, I'm going to take the full load amps on the secondary, which is 4511, divide that by 5.92, multiply that times 100, and I get 76,199 amps. So I would not base it upon the full load amps of 6014. I'm going to do the available fault current, which will be based upon the base kVA divided by the base, that impedance, 5.92, and I could lower that. I could do my 80-20, or my 80%. I can lower my 5.92 because of the error margins on, and I got to look up what the error margin is for a medium voltage transformer. Error margin for impedance on a medium voltage transformer. I know we typically use plus or minus 10%. It may be different for a medium voltage transformer. I just want to confirm that. But that would give me my maximum, and that would be based upon the full load amps of the 3750. All right, we got more comments. Dawn, back at it again. The secondary protection and conductors will be based on the actual calculated load. My load is, oh, we already said that. Sorry. Just saying there is no ampacity correction for the temperature rise of the transformer windings. I didn't say there was. I'm good with that. I agree with you. Bushings where the conductor is connected. No correction. I agree. I don't think I implied there would be, but if I did, then I agree with what Dawn was just saying. Even if you have to look at the temperature rise at the bushing, the exception to 310.14a2 will be get out of jail free card. I'm not sure what you're talking about. 310.14. 310.14a2. 310.14a2. 310.14. 310.14 is ampacities for conductors. A is general. 2, exception, where different ampacities apply to portions of a circuit, the higher ampacity. We weren't talking about ampacity, Dawn. We were talking about the insulation rating. Do I need a 90-degree C insulation? Do I need a higher degree? We weren't talking about ampacity. And I still have to do some homework. So if you have input on that, send me an email, because I'd love to have that discussion. Thank you, Laurel. I really appreciate that. So we did a little exploration of the code. And I let you know, guys and gals out there, don't forget your copy of 2026 Analysis of Changes. On the back, we got some good images. We got some cool stuff inside. We've got the way this is laid out. 120.7 power control systems. You've got a change at a glance. You have an analysis of the change. You have, and yeah, change at a glance and an analysis of the change. There's just a little sample. A lot of good stuff in here. I know we spent a lot of time. I can't wait for the PowerPoint. If you haven't seen the PowerPoint yet, I tell you, we put a lot of time into all this stuff. So cable ties. These are Article 100 definitions. They had some changes to cable ties and cable tie fixing devices. A lot of great stuff in this book. Get even a picture of Michael Hofkin on the back. All right, so hopefully, Steve, thank you. Thanks for the chats. Dawn and Laurel and Steve, Andrew Casnay. Who else did we have here? Chatting it up a bit. We had Laurel, we had Vince B, Vinny B, Michael Hofkin in the house. And he's traveling for UL again. All right, so hopefully we got something out of this. We sparked your interest to read more and learn more about medium voltage transformers and some of those nuances. We did take a look at the National Electrical Code a little bit, and we had a lot of fun doing it. So I hope you got something out of today. I know I did. I know I got some homework, and I will bring you an update on my homework assignments soon. Thanks, everybody. Thanks for what you do for the electrical industry. Thanks for what you do for IAEI. And if you're not a member, don't forget to join. Make it a part of your career. It is a good career move to be a member of IAEI. It's helped my career, and I'm sure it will help yours as well. All right, take care, stay safe, and please stay healthy. Catch you next time.